teaspoon of water weighs 5 grams, you could balance it on one finger. Fill that same teaspoon somewhere else in the universe, and it would weigh more than every human being alive today. That's not an exaggeration invented for a thumbnail. It's a figure NASA uses to describe the interior of a neutron star. And the strange part isn't just that such material exists, it's that the universe builds it routinely using nothing but gravity and time. So tonight we're going to fill the same teaspoon over and over at different places in the cosmos and watch what happens to the number on the scale. Because that one number, density, quietly explains almost everything about how the universe is put together. Let's start with the emptiest spoonful you could ever collect. Scoop your teaspoon through the space between the stars, and you'd capture, on average, about 5 atoms of hydrogen. Not 5 grams, 5 atoms. The interstellar medium is a vacuum so extreme that the best laboratory vacuums on Earth look crowded next to it. Your spoonful would have a mass of roughly 8 trillionths of a trillionth of a gram, and yet that near nothing, spread across a galaxy, is where every star begins. Now let's fill the spoon from the sun. Here's the first surprise. The sun, on average, is not that dense. Scoop a teaspoon of typical solar material, and it weighs about 7 grams, barely heavier than water. The sun is enormous, but most of it is diffuse plasma. Dive to the core, though, where the pressure of an entire star bears down, and the same spoonful jumps to roughly 750 grams, about the weight of a full wine bottle in a teaspoon. That's around 13 times denser than lead, even though the core is still hydrogen and helium, the 2 lightest elements that exist. That detail matters because it reveals the rule this whole video runs on. Density isn't really about what something is made of. It's about how hard something is being squeezed. On Earth, the heaviest spoonful you can physically hold comes from osmium, the densest naturally occurring element. A teaspoon of it weighs about 113 grams. That is the ceiling for ordinary matter sitting on a table, because atoms themselves push back. Electrons refuse to be crowded, and that refusal is what makes solid objects solid. The rest of the story is about what happens when gravity wins that argument. When a star like our sun dies, it sheds its outer layers and leaves behind its exposed core a white dwarf, half the mass of the sun, compressed into a ball roughly the size of Earth. Fill your teaspoon there, and it weighs several tons. 1 spoonful, heavy as a pickup truck or an adult elephant. At this point, matter has stopped behaving normally. Atoms have been crushed so close together that the only thing preventing total collapse is a quantum rule. Electrons cannot occupy the same state, so they generate a pressure that has nothing to do with heat. A white dwarf isn't held up by burning anything. It's held up by mathematics. Astronomers first ran into this in the early 1900s with Sirius B, a faint companion of the brightest star in our sky. When they worked out its density, some of them simply didn't believe it. Arthur Eddington later wrote that the message the starlight carried, when decoded, said something like, "I'm made of material 3,000 times denser than anything you have ever come across." The initial reaction, he admitted, was to think the message was nonsense. It wasn't. It was just the beginning. Because when a star more than about 8 times the mass of the sun dies, electron pressure isn't enough. The core collapses in less than a second. Electrons are forced into protons, forming neutrons, and the empty space that makes up almost all of an atom is squeezed out of existence. What remains is a neutron star, around 1.4 times the mass of the sun, packed into a sphere roughly 20 kilometers or about 12 miles across, the size of a city containing more matter than our entire solar system's star. Now fill the teaspoon. At the average density of a neutron star, that spoonful weighs about 2 billion tons. NASA's more conservative phrasing is 1 billion tons, which is already the approximate mass of Mount Everest. And density inside a neutron star rises steeply toward the center, so a spoonful scooped from the deepest core, where matter may be several times denser still, could plausibly approach the 10 billion tons on our thumbnail? The honest answer is a range, because no one has ever weighed one spoonful at a time. Every figure comes from measuring the whole star and doing the division. Here's where we owe you a correction, though. The teaspoon is a cheat. You could never scoop this material. The star's surface gravity is around 100 billion times Earth's, and neutron-rich matter only exists because the weight of the entire star holds it together. Release a spoonful from that pressure, and it wouldn't sit politely in your kitchen. It would expand violently, essentially detonating, and its free neutrons would decay into a spray of radiation. The teaspoon isn't the sample you could take. It's a unit of disbelief. And even now, we don't fully know what's inside. NASA's NICER telescope on the International Space Station has spent years measuring the sizes of neutron stars precisely because scientists cannot agree on how matter behaves at these densities. Some models predict the cores contain matter dissolved into free quarks, a state that may exist nowhere else in the universe. That question is still open. A teaspoon from the very center might be the most exotic substance reality can produce. Might be, because there is one object denser than a neutron star, and this is where the story folds back on itself. Squeeze a neutron star any further, and it becomes a black hole, an object so dense it has, in a sense, no surface and no spoonful to take. Near the singularity, density stops being a number physics can even describe. But average a black hole's mass over the volume inside its event horizon, and something absurd happens. The bigger the black hole, the lower that average density gets. For the most gigantic black holes known, monsters of tens of billions of solar masses, the average density inside the horizon works out to less than the air in your kitchen. Which means, by that admittedly loose accounting, a teaspoon of the most massive objects in the universe weighs less than the teaspoon of water we started with. So here's the verdict. The title is true, and then some. The same 5 milliliters can hold 5 atoms, 5 grams, or several billion tons, and every one of those spoonfuls obeys the same physics. Density isn't a property of stuff. It's a record of how hard gravity has argued with matter, and how much matter has managed to resist. We are, all of us, made of the spoonfuls in the middle, light enough to stand up, dense enough to exist. Here's the question for the comments. If you could safely examine one spoonful from anywhere in the universe, which would you choose, and what would you want it to tell us?